All right, folks, Mr. Bucko here with a couple of examples and vocabulary words for section 9.1 in advanced algebra, which is on exponential growth. So a couple of vocabulary words that we need to be familiar with are exponential function, an exponential curve, and then a growth factor. So an exponential function, the definition of an exponential function is a function that we're going to call f with the equation f of x is equal to a times b to the x power. And it has certain conditions here where a cannot be 0, b needs to be bigger than 1, or I'm sorry, bigger than 0, and b cannot be 1 at all. So this is what an exponential function is, where we have a value a that is our starting value, and it can't be 0, because if a is 0, then this whole thing goes away, and then it's no longer a function or anything, because if we multiply anything by 0, it's gone. So a can't be 0, b needs to be a number that's bigger than 0, and it can't be 1, because if b is 1, then this value just stays the same and it's equal to a the whole time. So kind of like y can't be 0, a can't be 0, b can't be 1, because then it's not changing, it's just staying at 1. And an exponential function can kind of be analyzed or noticed because the variable is the exponent. So x can be any number here, and there are no restrictions on x. That's the variable, and that's what makes this an exponential function. So we have a times b to the x power, and it's just b to the exponent of x. It's not a, it's just b. So that's what an exponential function looks like. It'll make more sense maybe when we actually put numbers in here as to what that looks like, but these are the conditions that have to be true to make this an exponential function. Now, an exponential curve is just the graph of the exponential function. So once you have values for a and b, you plug it into the function, and then you graph the function. What you get is an exponential curve. It's the graph of this. What does the pattern look like? And we'll see an example of that here momentarily. And then the growth factor in the exponential function y equals a times b to the x, with a being bigger than 0, is the base b. So the b right here is called the growth factor. That's what's causing the change or the pattern to occur. That's what we're multiplying our initial value a by as we go. This will perhaps make a little bit more sense when some of this stuff with actual numbers also. These are the three words that we need to be familiar with: exponential function, exponential curve, and the growth factor. And these all apply to exponential function and exponential growth. And we'll see in a couple minutes exponential decay as well. Our first example asks us to use a cast. Now, we're not going to use a cast. We're not using a cast, but we're still going to use the function here. So using the cast is going to result in us not necessarily knowing some of the answers here that are forthcoming, but we'll analyze that when we get there. So we have this function f of t is equal to 24 times 3.5 to the t power. This is an exponential function. I know that it's an exponential function because the variable is an exponent. The variable t is an exponent, and we're going to estimate the number of rabbits after 2 years and 3 months. So this is totally out of context, so let me put it into context for you. This is a function modeling the amount of rabbits after so much time. So when it says the number of rabbits, that's what this function is telling us. And what these numbers represent here is that we started with 24 rabbits. Let's say there's a population of rabbits. It starts at 24. And then it's increasing, or it is tripling, or the population is changing by a factor of 3.5. So that means that after every time period, after every year is what the time period is, after every year, the population is being multiplied by 3.5. That's what's happening here. That's what this function is saying that is happening to this population of rabbits. And we want to find out or estimate the number of rabbits after 2 years and 3 months. So t is in years. So if we're going to take 2 years and 3 months, and plug that in to our function here, we have to change 2 years and 3 months into years. Well, 2 years and 3 months is equal to 2.25 years. So we take 2.25 and we plug it into our function. So we find f of 2.25. When we plug in 2.25 into our function, we get 24 equals 3.5 to the 2.25 power. We're going to need a calculator for this. I have no idea what 3.5 to the 2.25 power is. Turns out that it's 16.76. And then we're going to take 16.76 and multiply that by 24. Notice I just did 3.5 to the 2.25 because just the only base of the exponent is just the 3.5. Multiply those together and you get about 402.24 rabbits. So what this means is that there's about 402 rabbits, or about 400, depending upon what you rounded this decimal to, because 3.5 to the 2.25 isn't exactly 16.76. But after 2 years and 3 months, there's going to be approximately 402 rabbits if we started with 24 and it's 2 years and 3 months later. Now, obviously, that's just based on the pattern. Obviously, that means no rabbits are dying, which is not realistic, but just if this pattern continues, this is how many rabbits there would be based on this function. Now we're going to estimate the time to the nearest hundredth of a year when there will be 5,000 rabbits. So this is where we're going to need a CAS, and we're not going to use a CAS. So what we're going to do here is just plug it in and see what this looks like. So we want to know when are there going to be 5,000 rabbits. So when is the value of f of t going to be 5,000? So what that looks like is this. We want to know the rabbits are 5,000. What does t need to be? What's the value of t such that 24 times 3.5 to the t power is 5,000? This doesn't look like a solvable equation based on the information that we know about algebra at the moment. And this is where the CAS would come into play, because we could plug this into the CAS and just tell it to solve this equation for t. We're not going to do that. We're just going to leave this right now because we don't have the tools at the moment to solve this equation. So I'm not sure exactly what the nearest hundredth of a year is at when there will be 5,000 rabbits, because I'm not exactly sure at the moment how to solve this. We don't have the tools yet. So we're just going to leave it here. We could graph it and maybe figure it out, but that's not really rounding to the nearest hundredth of a year. So we're just going to leave this as is for the time being. And then we're going to use a graph of f to estimate the function at -1/2. So in the context of the rabbits, this might not make any sense, or it doesn't make any sense, because it's kind of like going back in time a half a year. But what we can do is look at what an exponential curve would look like. So I'm going to take this function, f of t equals 24 times 3.5 to the t power, and I just plugged it into Desmos here. So I just copied this right from Desmos, our graphing calculator online. And we get 24 times 3.5 to the x power. That's t. That's just what I put in for t for the variable. What this curve looks like is this. This right here is an exponential curve because this is the curve of 24 times 3.5 to the x power. And I don't know if you can see this, but the x-axis here goes from -2 to +2. Then the y-axis goes from 0 up to 100. So I just kind of modified that, especially for the f value that I'm looking for here. So this is an exponential curve of the function f of t equals 24 times 3.5 to the t power. And I have an x there because that's what I plugged in when I put it into Desmos. So that's what the curve looks like. We want to find out, well, what's the value, or what's the value of the function when t is negative, or in this case, x is -1/2. Well, x is -1/2. There's -2, so halfway would be -1's about right there. And then -1/2 is about right here. So again, we're asking to estimate this. So -1/2, go up to the graph. I'd say that's probably around maybe 15 or so. So the value of f of -1.2, according to our graph here, is about -15 based on our graph. And then this graph right here is an exponential curve.